This is the first video on electromagnetism for A-level physics. The aim of this video is to refresh on some GCSE electromagnetism, look at the problem with cutting field lines, and develop the idea of how much field passes through a loop, something that we call flux. So at GCSE we learn that voltage is induced when magnetic field lines are cut. When we move something through a magnetic field and cut those lines. Additionally, we learn that voltage induced is directly proportional to the rate at which field lines are cut. So that meaning if we cut lots of field lines very quickly, the voltage induced will be large. But if we don't cut many field lines and we cut them slowly, we take a long time to cut them, the voltage induced will be small. Now there is a slight problem here with this idea. It's not wrong, but the idea of cutting field lines is slightly misleading. So what we'll do is we'll investigate something called magnetic flux. By considering a loop. So basically imagine a metal wire that's shaped into a rectangle so it comes back on itself. And we'll consider the amount of field that passes through that. So let's go through that. So case 1. So we'll need a region with a uniform magnetic field. So we'll draw that out. Here we have our uniform magnetic field strength. We just need to go over what a few things mean here. These circles with crosses in them, they mean that the magnetic field is directed into the page. You can see that these magnetic field lines, the crosses, are evenly spaced, which means the magnetic field is uniform. It's got the same strength throughout it. The dashed pink rectangle around the edge of this is just to show the extent of the field, the space that it takes up. What we now need to do is we need to put a loop inside this field. So let's place a rectangular loop in here, like this. There we go. And what we're then going to do is move this loop in one direction. So we'll move it to the right. If we pick the loop up and move it to the right, it will end up in this new position here. And to have been moved to the right, like this, the field lines here, these three, must have been cut, but by the leading edge of this, the edge on the right. And additionally, these field lines here must have been cut as the trailing edge, the left edge of the loop, cut through them. And so we'll use the GCSE idea that cutting magnetic field lines induces a voltage, and we'll draw this out. So we'll draw our loop again. I'm just going to draw it with slight change. If cutting field lines induces a voltage, we can say that each edge of the loop, each vertical edge, is going to act as a source of voltage because it's had a voltage induced across it. And now we can see the problem. Both these will have the same voltage because they cut the same number of field lines in the same amount of time. Well, these two batteries, they look like they're directed the same way, but the one on the left is going to try to direct a current this way, and the one on the right is going to try to direct a current the other way. ultimately, as they're opposed to each other and they're the same, they're going to wipe each other out, so there's no overall effect. No effect produced. Really what we're saying there is no voltage is induced. So that's kind of what I mean by the problem with the idea of just cutting magnetic field lines. So let's go a little bit further and consider another case, case 2, where we don't really have this problem in the same way. So again, we're going to need another magnetic field. Here we have our magnetic field, and what we're going to do slightly differently here is we're just going to reposition the loop at the edge of the field. So I'll draw the loop in, much the same size loop. There's our loop sitting right at the edge of the field, and just like last time, we're going to move this to the right. There's the arrow showing that. So let's take this over to the right, or slide over and draw in the new position of the loop. It's moved over like this. Now things are slightly different here. On the right side of the loop, it didn't cut any field lines, right? This part here, it didn't cut any field lines. It moved out into a region where there is no magnetic field. But on the other side here, the left edge, right, these parts, that part, cut magnetic field lines. It cut these field lines. So again, we'll try the GCSE idea. So if those field lines have been cut, then we must have induced a voltage in that side of the loop, but we didn't induce a voltage on the other side of the loop. Let's look at the loop with batteries put in place of EMFs. So redrawing the loop, we've got on the right side, we've got a battery because a voltage was induced, but that's the left side, and then on the right side that hasn't happened because the right side did not cut any field lines. So now this would drive a current if the circuit's complete, and it's not opposed by something on the other side, so that there is a net effect. Overall, we do end up having some voltage induced here. So we need to be able to compare these two cases to each other. There's, one of them ends up inducing a voltage, and the first one did not. So we should focus on the difference. Okay. So why these two cases differed. Right. What we'll need to do is draw each of the two cases again, but in miniature, so we can compare them side by side. And now we've got the two cases side by side, we can compare them to each other. What we need to focus on is the number of field lines that pass through the loop. If we look at case 1, so in case 1 has, so to start with, it's got 12 field lines passing through it. And then, after being moved right, that is into the green position. You see the green loop is just the same as the white loop moved over by a unit of space. Moved right, it's still, and that's the important issue, it still has 12 field lines passing through. So that didn't change, and that side's associated with making a voltage of 0, nothing happening. So we should very much associate these two things with each other. Still, no change, no voltage. On the other side, it's much the same. So case 2, to start with, start at 12 field lines. Same as before, they started out in an identical fashion, but then it ends with 9 field lines. What we can conclude from this, and then also we see that the voltage is, it's not 0 there. We do actually induce some voltage. We can see here that if the amount of field that passes through a loop changes, then we end up inducing a voltage. And instead of saying the amount of field, we have a way of referring to that in physics, and that is known as the magnetic flux. Yeah. So we'll say that the amount of field or magnetic flux that passes through a field dictates voltage. Right, the really important point is, if flux changes, then a voltage will be induced. That's the key point here. That's what we've been building up to by looking at these different loops and treating them like they've got batteries on either side, because each side induces a voltage. Okay, and then one final point is that as voltage is directly proportional to the rate at which field lines are cut, right, that's the GCSE idea, it follows that voltage is directly proportional to the rate of change of flux. So that's another key idea. Voltage is directly proportional to the rate of change of flux. What we've basically done in this video is just move on from the GCSE understanding where we consider cutting magnetic field lines to a clearer idea where actually we deal with flux through a loop changing. In the next video we'll discuss flux in greater detail, and in the third video we'll discuss flux when angles other than 90 degrees are brought into the problem. Okay, that's that.